Hey, Mr. Harridan here. We're going to go over calculating enthalpy changes of reactions. Deciding if the heat is reactant or product. If heat is listed as a product, the reaction is exothermic. Delta H here is negative, and the diagram looks something like that if it's exo. And heat will be listed as a product, meaning that heat is leaving the system here, which means the amount of energy released as bonds were formed was greater than the amount of energy taken in when bonds were broken. If heat is listed as a reactant, the reaction will be endothermic, where delta H is positive, and the graph looks something like this. Okay? Which means that heat was entering the system, which means that more energy was taken in to break bonds than the energy released to form bonds. Okay? Identify the following reactions as exothermic or endothermic. So here we see that's 2,220 joules in the kilojoules. It's on the product side. If it is on the product side, this is an exothermic reaction. Notice that heat is always listed as positive in a reaction. Okay? You don't write negative 2,220 joules. The negative sign just tells me which side the energy is on. Over here, we have 1,800, yeah. Learn how to read, Mr. Harridan. That would be nice. 180.7 kilojoules. This is on the reactant side. Since this is on the reactant side here, this reaction is endothermic, since heat is entering the system. Okay? But notice that we can list the heat as part of the reaction, which means we can write the mole ratios, which is the infamous wham 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 from Mr. Harridan here. So, since it is part of the reaction here, we can write 89.3 kilojoules per 1 mole of carbon, or 89.3 kilojoules per 2 moles of sulfur, or 89.3 kilojoules per 1 mole of carbon disulfide. We can do some wham 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 some ratios with these. Okay? And that's what we're going to have to do here when we are calculating the enthalpy change for a given reaction. You're going to have to put the energy in the reaction, and then we're going to do some classic stoichiometry. Let me show you how this is done. From the reaction above, calculate the amount of heat change in kJs. We're looking for the kJs. Gotta find those kJs, because everybody loves the kJs. Okay. When 5.66 grams of carbon disulfide is formed. So we're going to start off with 5.66 grams of carbon disulfide. We are going to try to find the kJs. Okay? Step 1. When in doubt, go to moles. Grams on the top, grams on the bottom. What are we going to convert to? Moles. Swish, swish. What does the tape say? Tape says 1 mole. Grams, molar mass, 76.15 for carbon disulfide. Okay, now we are going to do the reaction, which is the wham 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 wham. Moles on the top, moles on the bottom. What are we going to convert to? kJs. Swish, swish. This is moles of carbon disulfide, so this is moles of carbon disulfide. Now we're looking at the reaction here. Wham, 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 wham. 1. Wham, 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 wham. 89.3. That's what goes there. Multiply and divide, multiply and divide. 66.4 kilojoules. This is positive because it is endothermic. Endothermic, positive, delta H, Okay. See? Easily done. Let's do another one, since we're having so much fun doing this. The reaction above, this one is endo, remember, because delta H is positive, and the heat is listed on the reactant side. Using the reaction above, calculate the heat change in kilojoules when 16.83 grams of sulfur reacts with carbon to form carbon disulfide. So here we are going to start off with 16.83 grams of carbon disulfide. We are looking for the kJs. Step 1. Gotta do the tape. Grams on the top, grams on the bottom. What are we going to convert to? Moles. Because when in doubt, don't know what you're doing, go to moles. 1 mole goes right here. Why did I write carbon disulfide, Mr. Harridan? It doesn't say carbon disulfide, Mr. Harridan. Come on. Come on. It says sulfur. Learn to read, Mr. Harridan. Okay. So this is grams of sulfur down here. Molar mass of sulfur is 32.07. Then we have to do our reaction. Have to do our wham, 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 wham. Moles on the top, moles on the bottom. What am I going to convert to? kJs. So this is moles of sulfur and moles of sulfur. Reaction says wham, 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 wham. 2 moles of sulfur. Wham, 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 wham. 89.3 kJs. And if I was to round this answer for sig figs, because I didn't do that in my notes, I get positive 23.43 kJs. Easily done. Let's check out the next problem. The production of iron carbon dioxide from iron 3 oxide and carbon monoxide has an enthalpy value of heat of reaction, negative 26.3. Calculate the heat change in kilojoules when 3.4 grams of carbon monoxide reacts with excess iron oxide. Okay, so we have to place the energy in the reaction first, because we can't do any wham, 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 whams unless we put the energy in the reaction. Since this is exothermic, we all know it's going on the product side. So we're going to write positive 26.3 kilojoules right here. Remember, this is exothermic and delta H is negative. So we are going to start off with 3.40 grams of carbon monoxide. We are going to convert that to kilojoules. Again, I'm going to need 2 steps. Got to do the tape. Got to do the reaction. Grams on the top, grams on the bottom. What are we going to convert to? Moles. Tape says 1 mole. Grams, molar mass of carbon monoxide is 28.01. Okay, then we do our reaction. Moles of carbon monoxide on the top, moles of carbon monoxide on the bottom. What are we going to convert to? kJs. Wham, 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 wham. 3. Wham, 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 wham. Negative 26.3. It's negative because it's exothermic. Negative delta H. And I get an answer of negative 1.06 kilojoules. Easily done. Okay, one more problem we gotta do. Oh, the thermite reaction. Everybody loves a great thermite reaction, right? You know, it's one of those hot reactions that melts through everything, you know, because it produces a lot of heat, you know. Negative 849 kilojoules is a lot of joules. It's 849,000 joules. That's a lot of heat. Okay. Determine the mass of solid aluminum that would need to react to have a heat change of negative 780 kilojoules to occur. So in this problem here, we are going to start off with the 780 negative kilojoules. We have to put our heat of reaction in our reaction. Remember that this is exothermic. Delta H is negative. So this 849 is going to go on the product side. We are looking for the grams of aluminum. So in this problem here, we are going to do the whams first. We got the kJs. So we need to put kJs down here. And then we're going to put moles up here. Wham, 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 wham. Negative 849. Wham, 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 wham. 2. Remember, that's the reaction. Then we have to do the tape, because we're going to grams. Moles on the top. Moles of aluminum, of course. Moles of aluminum on the bottom. What are we going to convert to? Grams of aluminum. Swish, 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 swish. Okay. 1 mole, 26.98 grams. I should solve this problem to make sure I get the right answer. And I get 49.6 grams of aluminum. You guys are champions. The legend is out.